Hello everyone, and welcome back to another video where we are going to be evaluating this fun little sum from Math Stack Exchange. And the first thing we're going to do is take a look at this zeta term right here. What we're going to do is just expand it. So we know that zeta is just equal to the sum from k equals 1 to infinity of 1 over k, and in this case, to some s. And substituting this in, we have the following. So we still have our sum from s equals 3 to infinity of negative 1 to the s minus 1. But then now we have times our sum from k equals 1 to infinity of 1 over k to some s. And what you might see here is that we have, well, two sums obviously, but because these two sums are really independent of each other, so for example, there's no s in the upper bound here, what we can do is just reverse the order of the sums. So what we can say is that this is now equal to, or this is the same thing as, the sum from k equals 1 to infinity of the sum from s equals 3 to infinity of negative 1 to the s minus 1, and then divided by k to some s. And what you'll see here is something that looks somewhat familiar. If we drop one of the negative ones to the outside, throw a negative there, you'll see that we both have our negative 1 and our k are to the s power. So we can write that as just one term. We can just write this as negative k to the negative s. And what we can see this as is just a geometric series. But because we're starting from s equals 3 as opposed to s equals 0, our formula is going to take on a little bit different of an appearance. So what we're going to have, you might remember this from a Calc 2 class or something, is the following. We're going to have negative k to the 3, or the negative 3, because that right there is our first term in the series, and then divided by 1 minus whatever our base is right here. In this case, it's negative k, so it's actually going to be a plus 1 over k. 1 over because we have the negative right there. So what's one way we can simplify this? Well, we can distribute all of this right here. So this is equal to, scrolling on over, this right here is equal to, well, negative 1 to the negative 3 is just going to be negative 1 still. So we still have a negative 1, but then we can distribute this k to the third in the denominator. So we have a k to the third, then times the 1 plus 1 over k. And we can just rewrite this distributing a single k as 1 plus k, and then change this to the power of 2. And this right here is our new sum, because you'll remember that we're also summing from k equals 1 to infinity. So now what we have is the sum from k equals 1 to infinity, and you'll see that the negative here and the negative here actually cancel. So we have the sum from k equals 1 to infinity of 1 over k squared, and then 1 plus k. And you might remember the sum from a previous video, but let's evaluate this again. And to do that, we're going to do partial fractions. So what we can say is that 1 over k squared times 1 plus k is equal to some ak plus b over k squared plus some c over k plus 1. And cross multiplying everything, we find that ak plus b, so ak plus b times k plus 1 plus k ck squared is just going to be equal to 1. So now all we have to do is plug in values for k to solve for our coefficients a, b, and c. So if we let k equal, say, negative 1, we see that this whole term right here just goes to 0, and that we're multiplying our c by a negative 1 squared, which is just 1. So we have a c times 1 equals 1, so we know that c is just going to be equal to 1. And now let's take a look at b. Well, similarly, we can plug in k equals 0 for, we can just plug in k equals 0, and you'll see that this term right here goes to 0, and so does this one right here, this term with the a in it. So what we're left with then is just this term right here, which is just going to be 1, because, 1 plus 0 is just 1. So we have b also equals 1. So b equals 1. So now all we have to do is find a value for k, plug it in, and solve for a. So for the sake of simplicity, I'll do 2. So plugging k equals 2, what we end up getting is 2k plus, well, b is just 1, and then times k plus 1, but we're plugging in 2, so that's times 3. And then we have a plus ck squared, but c is just 1, and 2 squared is just going to be 4, so plus 4 equals 1. You'll see here that we have 2k plus 1 then is just going to be equal to negative 1, meaning that, or sorry, this should be an a right here. No, that's annoying. But just doing a little bit of algebra, we find that a right here is just going to be equal to negative 1. So a is equal to negative 1. And substituting all of this back into our original sum right here, let's see what we find. So this right here is now equal to still the sum from k equals 1 to infinity, but now we have, so negative k plus 1 over k squared, and then plus 1 over k plus 1. And we can simplify this actually quite a bit. We can split this up into two sums. So we say this is the sum from k equals 1 to infinity of 1 over k squared. We can evaluate that. But then we also have plus the sum from k equals, I'll move it on over a little bit more, k equals 1 to infinity still, of course, of 1 plus k plus 1, but then minus this 1 over k term because, well, the exponents here are going to cancel a little bit. So straight off the bat, we can just say that this sum right here is pi squared over 6. We know that. That's kind of famous. But the sum on the right, one way we can actually evaluate it is by taking a look at specifically this part right here. We can rewrite this as, the first part isn't going to change, so we have the sum from k equals 1 to infinity of 1 over k plus 1. But this next term right here we can actually reindex as another sum. So we can say this is now the sum from k equals 0 to infinity of 1 over k plus 1. And you'll see here that it'd be really nice if you could get these two things to cancel. The only thing that isn't allowing them to cancel completely is the fact that one starts at k equals 1 and this starts at k equals 0. So one way we can reconcile that is just rewriting this sum on the right here, just taking the first term of the series and then adding the rest of it, because after all, that is just what a sum is. So what we can say then is that this right here, plugging in 0, is just going to be 1 and then plus the sum from k equals 1 to infinity, 1 plus k. But you'll see here that this and that are just going to cancel, because we have this good old minus sign right there, which leaves us with this pi squared over 6 on the left, so pi squared over 6 on the left, and this 1 right here, which because of this aforementioned negative, is just going to be minus 1. So the value of this awesome zeta sum is just going to be pi squared on 6 minus 1. And I hope you all enjoyed this shorter video than normal. Probably makes up for the longer complex analysis one. But at any rate, I hope you all enjoyed, and I will see you in the next one. Bye!